Lesson 3.9, Applications of the Derivative. We're going to start with some physics applications, which might be very familiar to you, but how we cover them in calculus for some of these problems is done slightly differently. And just so that you know, physics formulas are not allowed on the AP exam. So if you want to use your physics formulas, you can use them to check your information. Definitions to start with is talking about motion when a particle or an object is speeding up versus slowing down. In the calculus perspective, we check the signs of both velocity and acceleration. If the signs are the same, they're working together, that's going to cause your object to speed up. If they have opposite signs, that's what causes it to slow down. Distance versus displacement is next. Distance is literally how far you have literally traveled in all directions. I have some steps here that I'm going to use later when we calculate the total distance an object has covered, so you can read through those. Versus the displacement, and that change, or the overall change in the object from where it ends to where it starts. We have a particle moving along a line, and this is our position function here. S is going to be measured in feet, T is going to be measured in seconds. First thing we're going to do when we analyze motion is we analyze the velocity, because velocity tells me not only how fast I am traveling, it is the rate of change of the position function, but also its direction, and that will matter on many occasions. Velocity, straight out using derivative, would be 6t to the second minus 42t plus 60. Find the velocity at time t equals 1 second. In calculus, just so you know, what you have to do is you have to identify what you are finding. So I'm finding velocity at time 1. I don't literally have to go and show a 1 being plugged into every single term. I am allowed to say v at 1, and then this tells me, especially on graphing calculator oriented problems, it tells me I'm analyzing this function at a value of 1. And whether you do it by hand or you do it on your calculator, you get 160 feet per second, because that is a unit rate. Find all times t when the particle is at rest, when velocity is equal to 0. So particles stop when they have 0 velocity. In our case, we're going to have 6t squared minus 42t plus 60 equaling 0. Or you could have, as a first step, notice that all of these are divisible by 6 and pulled out the 6 as your first line of work. The only thing left is to factor this down further. And we can get our 2 times when the velocity is 0. Okay? Now, depending on the problem, if it was graphing calculator oriented, you could go from here to here and just give your answer. If it's non-calculator oriented, then you're showing the work to get through the factoring to move those. When is the particle moving in the positive direction? Moving in a positive direction means the velocity is positive, or v of t is greater than 0. Well, if I'm looking here, my velocity function, I have this version of it, this version of it, and this version of it. The easiest format for working with defining if particles are moving right or left is to look at the factored form of a derivative. And what you do is you plug in the key times when your particle is stopped, because when it's stopped, a lot of times it'll stop and change its direction, or it could just be paused and just stop and then move on its little path. And then, because it's an application problem, that means that I can't have negative numbers. So I'm going to say, okay, I'm going to stop here at 0. When is the particle moving in the positive direction? I would need to have a positive velocity. So I'm going to do what's called a sign chart to determine the signs of the velocity. To do that, I'm going to take numbers in these different intervals and plug them into the factored form of the velocity. If I take a 1 and I plug a 1 in, negative times negative, that means this region of the graph is positive from 0 to 2. From 2 to 5, if I test like 3 or 4, this is negative, this is positive. Negative times positive is a negative. That region of the graph is negative. To the right of 5, if I test 6, positive times positive, this region is positive. And yes, you only have to do one sign per region, but for something that's coming up further, you'll see why I do multiple. So when is it moving in a positive direction? Well, I have to start at 0. So I look at 0 in the velocity function. If you plug in 0, it's a positive 60. So that means at 60, at 0, I have a positive velocity. And I have a positive velocity until I get to 2, at which point it is 0 velocity. So we have that open, joined with the 0 for velocity at 5, and then when is it positive again? Forevermore. Find the acceleration at time t. A of t is the derivative of velocity. So I'm going to derive and get 12t minus 42 for the acceleration of the particle at any time t. Then I want to know, when is the particle speeding up versus, slowing down? This one just wants speeding up. I have to look at the signs of both velocity and acceleration. Well, velocity is done up here, so I'm going to bring those down. Then acceleration is going to be done next. And the acceleration, starting at 0 again. But what do I have for when the acceleration is 0? So I'm going to go back over here and use my calculator, set the acceleration equal to 0, and I noticed that I would get 42/12. So you can either literally leave it as 42/12, you can convert it to 7/2, you can convert it to 3.5, whichever one you would like to do. You put that on, that's when the acceleration is 0. Then I test between 0 and 7/2, say like at 1. If I plug 1 into the acceleration function, it is negative. So this region right here is negative. So hopefully you can start to see the value of putting multiple signs in. Whereas to the right of 7/2, say I take 5, that's 60 minus 42, that's a positive number. Particle will be speeding up when the velocity and the acceleration have the same sign. Well, these are opposite in sign. Then I look at the next region, they're both negative. So starting from 2 and going to 7/2, that would be my first interval. And just so you know, sign charts are a tool for you to use, but it is not looked at on the AP exam as evidence for why something occurs. So they are very helpful tools, but they are not used as evidence. So I'm going to go here and I'm going to say the velocity is less than 0 and the acceleration is less than 0, interpreting my sign charts. Then there's another region where it would be speeding up. Well, I check my signs, negative, 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 positive, positive, positive. So from 5 on, we are speeding up because velocity is greater than 0 and acceleration is greater than 0. You have to identify signs to justify speeding up or slowing down. Drawing a diagram to represent the motion. Well, if I look at the velocity tells me the motion. It goes to the right, it goes to the left, it goes to the right. So I'm going to leave some space up above, and I'm going to draw a number line. And it goes right, left, right. So I'm going to go above the number line and put a little dot representing my particle. And I'm going to say, okay, at time 0, it's here. Well, where is it at time 0? Go back to the position function, plug in 0, and you get 3. While I'm working on this one, I'm going to work on this one simultaneously, because as it moves, it goes a certain distance, and I'm going to need to calculate the distance according to that process I gave you up above. So what I'm going to do is I'm going to look at t and s of t at critical values. So at the start, we are at 3 feet. So I'm going to put that in because that will matter for distance. Then I look back at velocity. It's going left until it gets to, oops, sorry, I skipped the first part. It goes right until it gets to 2 seconds. So at 2 seconds, what is my position? So I plug 2 into the position function, and I get back 55. So it goes to the right until it reaches 55 feet, because this is a position function, or not function, diagram, or what they also call it is a schematic. So a diagram is also called, if you see this word, a schematic. At 55, which is at 2 seconds, it's turning. So I'm going to identify my turn here at 55 feet. Then I go back to velocity, and it changes its direction again after 5 seconds. So I'm going to plug 5 into the position function. It makes it all the way back to 28. So I'm going to go all the way back, flip. This is t equaling 5, and then I'm going to line this up, and we'll call this 28. Velocity forevermore is going to the right, so we represent it going to the right. So the original is a cubic, and this is kind of a cubic being drawn as we trace through. To find the distance during the first 8 seconds, since it does not turn again, I take 8 and I plug it in. I get 163. Total distance. You're going to figure out how far it moves from piece to piece. So 3 to 55, it moves 52 feet. It's working backwards, but still I want to know what is the number of feet. It's 27 feet. And then how many feet this way? 135 feet. My total distance is 214 feet. Oops, sorry about that. Give you a minute there. We're going to flip. You want to grab your graphing calculator if you don't already have it for something I'm going to show you in this next part. So for this one, we have a projectile. It's fired vertically upwards, and it gives us some information so we can put together, and eventually once we learn integration techniques, we'll learn how to put these together to make the position function. What we care about right now is just using the position function. Part 1, how long will it take for the projectile to reach its maximum height? Well, if I have a quadratic and it's got a negative coefficient, that means it's looking something like this. Its maximum height is actually found at the vertex. So I am looking essentially for the vertex, but I'm going to do it from a calculus perspective. Well, when it reaches the maximum height, it's changing its direction. So it goes from having a positive velocity to a negative velocity. That means at the maximum, velocity is equal to 0. Well, I have to find the velocity so that I can find how long it takes. My velocity function would be negative 9.8t plus 49. I'm going to set that equal to 0. And then solving for t, we get 5 seconds. What is the maximum height? To do this one, we're identifying to find the maximum height. Height is position. So I'm going to identify I'm using function s, and I'm inputting my value of 5, and then as long as it's a graphing calculator, even if it's not, you are allowed to just identify what your answer is, and hopefully we match with 272.5 meters for that maximum height. How long will it take for the projectile to hit the ground? Well, when it hits the ground, it has a particular height. That height is 0. So I'm going to start by acknowledging the first thing I'm doing is I'm looking for when the position function is equal to 0. As long as you identify what you're thinking in your brain and what you're analyzing, then you can take your graphing calculator, plug in s, and find the 0 of the function. So if I plug in x, negative 4.9x squared plus 49x plus 150. I'm going to zoom fit it just to start. And zoom fit is not looking so good. I'm not seeing enough over to the right. So I'm going to change it from negative 10 to, I'm going to go like 25. Let's see if that works better. I'm going to go by 5s, and then the y min, I hate when it does things like that, and so I'm going to go negative 400 to 300 by 100s. I like my stuff balanced. Alright, I can see my nice upside down quadratic. I'm looking for when that position is 0. So I want the 0 of the function, which is in this calculate menu. Oops, can't see it. The calculate menu, which is above trace. So I'm going to say second trace to get to the calculate menu. Option number 2 is to find the 0 of the function. I don't care about this 0 because that would be negative time. Right now my cursor is flashing here. I'm going to hit enter, and then I'm going to scoot along the curve until I cross the x-axis. Once I have crossed, I'm going to hit enter, and then just hit enter again. So the 0 of my function, or when it hits the ground, is at 12 point, so I'm going to now identify t to go along with this, is 12.457 to 3-place decimal accuracy. Have to have 3-place decimal accuracy. Now a cool feature is that if you put in x back in the home screen, it retains the value it just found, which is a very nice feature. You can also do things like store the value to variables. You can let me know in class if you've done this or haven't done it, and I can show you how to store. Part D, what will be its speed at impact? Speed doesn't take into account direction, just the amount of the rate. So speed is defined as the absolute value of velocity. So the speed at impact means I am finding the absolute value of v at 12.457. Now even though I'm writing 12.457, I am not using 12.457. I'm using my stored value, because as you progress through parts, you have to have 3-place decimal accuracy for each part. If you use rounded values, you tend to lose your accuracy in your end answers, and you will not earn the point for the answer. So I'm taking that number, and I want to plug it into my velocity function. Well, I can take and make things positive at the end. I'm going to go back up here to my velocity equation, which is right here, and I'm going to say negative 9.8 x to represent the time when the particle hit the ground, plus 49. Hit enter, and then I just have to make it positive, and I'm getting 73.082 meters per second for my speed. This is the graph of the velocity function, and it's saying when is the particle slowing down. So in order to slow down, velocity and acceleration have to be opposite in sign. So I'm going to start and work my way left to right. From 0 until about 1, the velocity is positive. The acceleration, we said, was the derivative of the velocity. Well, if I look at the slopes here, those are all negative because this function is decreasing, so it would have negative slopes. So I'm going to say I am slowing down from 0 until 1 because the velocity was greater than 0, but the acceleration is less than 0. Then I'm analyzing my next piece. Velocity now moves below, but it's still decreasing, which means the acceleration or the derivative would all be negative. So these are matching signs. Until I turn the corner here, velocity is still negative, but now I am increasing. If I'm increasing, that means the acceleration is positive. So from 2 until 3, the velocity is less than 0, but the acceleration is greater than 0, having opposite signs. And then above, it's a positive amount because I'm above, and then it's increasing, so the acceleration would be positive. You can take a moment and read through this, pause the video, and then start it when you're ready. How many units of sulfuric acid are sold daily to maximize the profit? Anytime you are maximizing or minimizing, that means I want to take the derivative, and if I'm at a max or a min, at a max, slope is 0. At a min, slope is 0. So maximizing and minimizing is all about derivatives equaling 0. Well, who am I deriving? I'm deriving profit. So I have to create a profit equation. Well, profit is found by taking your revenue, that means the amount of money you take in, and subtracting out your cost. In our case, to find the revenue, how much money we're taking in, well, we look at what we sell it for. We're selling $100 per unit. $100 for each unit would be 100x. Minus the cost function is given to us. And then what happens is I want the derivative. Before I do any derivatives, I, as a general rule of thumb, will clean up any terms so that all like terms are together and I don't have any algebra to worry about. So my 100x minus a negative 50x gives me 150x. Then I go to minus 100,000, then minus the 0.0025x squared. Oops, I got a typo, I just realized that. This is a plus, and I wrote it down as a minus, so that's going to change. So that's a plus, and then that takes my first term now to a 50x. Sorry about that. P's derivative would be 50 going to 0 minus 0.005x, and then because it's the derivative and we're saying it's supposed to be at a maximum, I'm going to say link it to the fact that it has to equal 0. Then I solve for x and we get 10,000 units are what we are producing to maximize the profit. Take a moment and pause and read 8. To find C prime at 5,000, I'm going to first do C prime of x. C prime, go to that cost function up here, up at the top, and it would be 50 plus 0.005x is my cost function. The cost at 5,000 is going to be 75. Once I identified my function, then I'm allowed to plug into that given function and give the answer. Well, what does that mean? That's a derivative. That means an instantaneous rate or moment. So we're going to say when, at, on. So when the 5,000th unit is produced, the rate, because derivatives are rates, at which the, referring to our function, which is the cost function, is changing, or in this case, because it's positive, I'm going to say is increasing, but you can say is changing. And it's at $75 per unit. Because it's a derivative, it's a rate. So it's something per something. In 9, take a moment, pause the video, and read it. We're talking about the volume, and it's wanting to know about the volume, how it changes when the side length changes. So if it's changing, then that means derivative. That means a rate. So I want to find V prime of x. Well, since I'm talking about a box, I'm going to go back up and say V of x, the volume in a box. If it's a cube, which it is a cube, based on this, the formula is x cubed. So the V prime, the rate at which it's changing based on its side length, would be 3x squared. Finding V prime at 100 is going to give us 300. Take a moment, pause the video, and try your explanation before you hear mine. When the side length, because that's our input, is 100 millimeters, there's that at, when, or on kind of situation. It's a derivative, so we're going to say the rate at which the, and what's our concept? This one is volume, is changing at 300 millimeters cubed, because it's volume, per millimeter, because the input is based on the side length, which is the millimeters. Number 10, we are going to cross off for now and save it for section 4.6 because that's an optimization problem.